Alright, and so begins Lecture 9 on convergence. So here we're talking about convergence of sequences of real numbers. And so here's the definition. If we have a sub n a sequence in R, we say a sub n converges to a if for any epsilon greater than 0, there exists a natural number n, big N, such that when little n is bigger than big N, that implies that the absolute value of a sub n minus a is less than epsilon. And we write a sub n goes to a, or the limit as n goes to infinity of a sub n is equal to a when the above holds. So notice that this condition here essentially says that the distance between the real number a sub n and the real number a is less than epsilon. So in words, what this definition is saying is that if the terms in the sequence can be made arbitrarily close to the limiting value, if we go far enough out, then the limit exists and it goes to a. Essentially, that's the intuition here. Now, so here's an example. So this example is from your textbook, of course, and get that out of frame there. All right, yeah, good enough. Let a sub n equal 1 over n. Then let epsilon be greater than 0. By the Archimedean property, there exists a natural number n such that n is larger than 1 over epsilon, because that's a real number. So remember, Archimedean property says that there's a natural number beyond any real number. So solving that for epsilon gives us epsilon is greater than 1 over n. And so I've just introduced a little m so you can hear me better. If m is greater than or equal to n, then 1 over n is greater than or equal to 1 over m. And so a sub m minus 0 is equal to 1 over the absolute value of 1 over m, which is equal to 1 over m, which is less than or equal to 1 over n, which is less than epsilon. Hence the limit as m goes to infinity of 1 over m is equal to 0. I noticed I changed the limiting variable here to m. So I was an experiment. I wanted to see if it would help the talking about these examples better, and it did a little bit, but I'm going to revert back to n and big N, and we'll be okay. I'll try to say big N and little n as needed here. So let epsilon be greater than 0. Consider a sub n is 1 over n to the power alpha. So if epsilon is greater than 0, 1 over epsilon to the 1 over alpha power is positive, and so by the Archimedean property we can find a natural number that is bigger than 1 over epsilon to the 1 over alpha power. But then, if little n is larger than big N, then that means that little n is larger than 1 over epsilon to the 1 over alpha power. But you see, we can take this inequality right here, right? And we can raise it to the alpha power to get n to the alpha is greater than 1 over epsilon. I mean, so that's a little lemma, which I don't think we've ever proved, but you know, lemma a less than b, in you know, 0 less than a less than b implies a to the alpha less than b to the beta, or a to the alpha less than b to the alpha, rather, for alpha positive. I mean, you could write the lemma in a better way, neater handwriting, whatever, that's the idea. Anyway, so 1 over n to the alpha minus 0 is equal to 1 over n to the alpha. So we can drop the absolute value bars, is what I'm trying to say here. And then that's less than 1 over epsilon, which of course is equal to epsilon again. So there we have it. The a sub n minus the limiting value 0 has been shown to be less than epsilon for n beyond a certain big N. Therefore, by the definition of limit, the limit as n goes to infinity of 1 over n to the alpha is equal to a 0. So, okay, well, fine. Now, the first two examples are, in some sense, are not very good because I didn't show you the scratch work, right? And so I just kind of showed you proofs, and it may leave you wondering, well, how did you figure out what how do you formulate such a proof? Like, how do you figure out what big N is? You know, because those just kind of dropped from the air, from the ether, if you like. But what we actually do in practice to prove one of these is we look at this difference, a sub n minus our limiting value, and we set it less than epsilon, and then we make a choice. We figure out what big N we're going to need in order to make this inequality happen for the n which are larger than the little n. So let's look at an example that's done like that. So first of all, the example 3 in your textbook. 3n squared plus 4 divided by 2n squared plus n plus 5. Supposedly that goes to 3/2. Let's see why. So first thing I do is I look at the difference of a sub n and a, which here is this. And so to combine these terms, I make a common denominator. And what I've done is I've multiplied the first one by 2 and the last one by 2n squared plus n plus 5. So that's algebra. And when you work that algebra out, you get minus 3n minus 7 over twice times the 2n squared plus n plus 5. Now, when we hit the absolute value on this, the thing in the denominator is clearly positive, and the thing in the numerator is, well, if we factor out a minus 1, we can just get rid of the minus and use absolute value to just drop it, So there it is. And then, my target is to make this less than epsilon. So what I'm going to do is think about some steps I can make along the way to get there. So first of all, I'm going to try to clean this up so I can make my choice of epsilon as uncomplicated as possible. So that's the first thing, is try to make this smaller than something that's easier to kind of wrap our mind around. And so the first thing I can do is make the numerator larger. I can replace 7 with 7n. I can make the denominator smaller by dropping the not leading terms, the n and the 5. So I'm just left with 10n over 4n squared. And of course algebra reduces that to 5 over 2n. So we're going to be making the assumption that our little n is larger than our big N, which means that we can trade 1 over n for the larger 1 over big N. Because again, big N is smaller, so we're making the denominator smaller here. And great. And now we see how we should choose the big N. We need to choose big N such that 5 over 2 times big N is less than epsilon, right? And so we're going to be able to use the Archimedean property, much like we did in the previous 2 examples, to make that happen. Alright, so that's the scratch work. Now let me show you the proof. Remember, the way this game is played is the proof should be self-contained, alright? So we can't write scratch work and then halfway through decide we're going to do a proof. The proof needs to be written so that it's self-contained. In a pinch you could refer to a calculation in the scratch work, but it would have to be really, really clear what you meant. Otherwise I would take off points for sure. Just a warning. So let epsilon be greater than 0, and choose a natural number n such that 5 over 2 times epsilon is less than n by the Archimedean property. Suppose little n is larger than big N. So then 1 over little n is larger than 1 over little n, big N rather. So 5 over 2 times little n is less than or equal to 5 over twice big N, which by the way is less than, because, well, excuse me, this is less than that, so I'm making this as a larger quantity, right? Because I made the denominator smaller, right? So I get 5 over twice 5 over 2 epsilon, so the 5's cancel, the 2's cancel, and 1 over epsilon's epsilon again, so hooray. So, alright, we know that. So consider then the difference of a sub n and a, the alleged limiting value 3/2. And now we're just going to trace back through that algebra we already did. And so make the common denominator, cancel the things, get to the 3n minus 7, then drop the absolute values, right? And then, trade our 7 for our, so we go to 10n over 4n squared, which is equal to 5 over n, which is less than epsilon. Because I know this, right, because I just argued it up here. This is part of the proof. I'm relying on the reader reading the proof top to bottom. That's our custom. And so what's been said before is assumed to still hold unless it's been, unless it's been retired from the discussion, so to speak. Therefore, the limit as n goes to infinity of 3n squared plus 4 over 2n squared plus n plus 5 is equal to 3 halves by direct argument from the definition of the limit. Now, I may or may not actually write this sentence in a given proof. Sometimes I leave it to the reader to understand that's what's been done. It should be clear from the fact that I started with epsilon greater than 0, and I made a sequence of arguments which led to show that the absolute value of a sub n minus a was less than epsilon, so it should be clear enough what the proof was about. Now, some professors are more dogmatic about you writing everything out in words. I try to be cool, but there's something inherently uncool about this particular course. Sorry to say, but it is a proof course, and there's things we have to do. So let's see here. But it is exciting to be able to prove these things carefully, and there is great value in this kind of rigor that keeps us from making the mistakes that held back 19th century mathematicians for as long as it did. But there's a balance to be struck anyway between intuition and rigor. So one of the things I haven't explained yet at all is how to find the limit, right? Of course, I think you've already seen that in a previous, like Calc 2 probably. Basically, you look for leading terms, right? Divide the top and the bottom by the leading power, in this case n squared, and that gives you like 4 minus 1 over n squared divided by 3 minus 1 over n. And so if you think about n going to infinity, these get dropped to 0 and leaves you with 4/3, right? Now that's not a proof, that's just intuition at the moment. This could elevate to a proof once we had limit laws. And I'd write a little bit more, but at the moment, we're proving it by the definition, so let's do it. Actually, before we do it, we're going to look at the scratch work. Here's the scratch work. So I'm pretty sure it's 4/3. So I need to take a sub n minus 4/3. I need to make that less than epsilon for n larger than big N. And if you work out this algebra right here, right? If you work out that algebra right there, then offending smudge, get rid of it. Excuse me. Make a common denominator, cancel stuff, and so here notice that 4n minus 3 is clearly positive because if n is larger than 1, this is like 4 or 8 or 12 and so forth and so on. So it's pretty intuitively clear that that's positive. So I can drop the absolute value, and the denominator is obviously positive. So we go from there to there, from here to there rather. And then I've made the numerator larger by dropping the minus 3. And so then algebra says that's 4 over 9n, which we can make less than 4 over 9 times the big N. And I guess I'm using equals here usually. And then I can choose big N to be less than epsilon. That's what I want to do. All right, so there's the man behind the curtain, so to speak. Now let's actually look at the proof. Here is the proof. Let epsilon be greater than 0. Notice 4 over 9 epsilon is positive. Hence, by the Archimedean property, there exists big N and n such that 4 over 9 times epsilon is less than n. And therefore, 4 over 9 times big N is less than epsilon. So suppose n is a natural number and n is larger than big N. Then, by the algebra we just went through up there, a sub n minus 4/3 is equal to this, which make common denominators that, which simplifies to this, which is equal to that, which then we can make the numerator smaller, make the denominator, whoa, what happened to my denominator? Whoa. Whoa. Oh no, guys. I'm glossing over something here. I'm sorry. Let's think about this some more, see if we can fix it. See what I did here? This is not good. So 3n minus 1 dropping to 3n, is that a reasonable step? What would I be doing? I would be making the denominator going what? 3n minus 1 to 3n. That makes the denominator larger, right? Which makes the fraction smaller. Oh no! So this is not going to work. All right, so tell you what here. Let's fix it. So we have the absolute value of a sub n minus 4/3 is equal to, we worked it out, 4n minus 3 over 3n times 3n minus 1, right? Now what I suggest we do is just make a little creative accounting here. This is 3n minus 1. Let's see here. 4 times 3n, how can I say this? 4/3, 3n minus 1, and that will give me back the 4n. I just subtracted, I've got a minus 4/3 here. That's a minus 9/3, so I guess I still need a minus 5/3, yeah? I'm not sure this is going to work, I'm trying. Alright, so clearly that is less than 4/3 times 3n minus 1 over 3n times 3n minus 1, right? Because I just made the numerator larger by getting rid of that subtraction. And so now I can cancel these offending factors. And that gives me 4 over 9n. I can make that less than 4 over 9 times big N, or equal to. And I'm going to choose big N to be less than add epsilon. Alright, so here's the proof. Let epsilon be greater than 0. We choose n in the natural numbers such that, 4 over 9 times epsilon is less than big N, which of course implies that 4 over 9n is less than epsilon for our future reference. So suppose that little n is greater than or equal to big N, and calculate the absolute value of 4n squared minus 1 over 3n squared minus n minus 4/3. Well, that's equal to 3 times 4n squared minus 1 minus 4 times 3n squared minus n divided by 3 times 3n squared minus n, right? But that is equal to the absolute value. The 12s cancel, and we're left with minus 3 plus 4n, I believe. Right? Yeah. Divided by 3 times n times 3n minus 1. But that is pretty clearly equal to 4n minus 3 over 3n times 3n minus 1, because that's positive, and that is less than 4 times, well, rather 4/3, right, times 3n minus 1. So that keeps that 4n term, right? And I've just subtracted 4/3. I have 9/3 here, so I still need minus 5/3 to keep equality. I shouldn't say less than or equal to. This is just straight up equals at the moment. So this is equals. Alright, and now that's less than 4/3 3n minus 1 divided by 3n times 3n minus 1. Those cancel. And we're left with 4 over 9n. right? Now, that then in turn is what? Come on. That is less than 4 over 9 times big N, which we have just, constructed big N up here to be less than epsilon. So therefore, the limit as n goes to infinity of 4n squared minus 1 over 3n squared minus n is equal to 4/3. So, yeah. Sorry about that. See, that's the kind of mistake it's really easy to make in my previous, previous version of this example. All right. So it's so easy to make a careless mistake like that. You just get tricked into thinking that since you made it smaller, it works, right? But you got to be careful. The numerator we need to make smaller. Excuse me, we need to make the numerator larger. We need to make the denominator. See, I keep. It's a question of whether I'm reading it this way or that way, But to go to a larger fraction, we either need to make the denominator smaller, which I have not here, right? This is not smaller than that. Excuse me, I can't do it. This is not smaller than that. Anyway, I'm going to shut up about this before I do more damage. Next example. Again, intuition says that this limit dividing by n squared, we look at it, looks like it goes to 1/4. So we do the algebra, and so this time it's not so easy to drop the absolute value because the story changes when we go above or below 20, right? Like when we're below 20, this is positive. When we're above 20, this is negative. So in particular, this is the story, n less than 20, it's equal to that, and greater than 20, it's equal to that. So if we could just build the assumption that our big N is at least 20, then we could just think about this case. That's what we'll do. And so if we're larger than 20, then n minus 20 over 16n squared plus 4n is less than, notice that I made the numerator larger. I made the denominator, well, I didn't do anything yet. Now going from here to here, I canceled the n. And going from here to here, I made the denominator smaller, which makes the fraction larger. And so that's less than or equal to 1 over 16 big N, which is, I'm going to construct epsilon. I'm going to choose n to make that happen. Alright, so what I'm going to do is I'm going to say let n be the maximum of 20 and 1 over 16 epsilon. Well, that's not quite what I did. Let's read my proof. That was what I was going to do, but then as I was writing the proof, I decided that wasn't, it's just still kind of left me things to explain, so here's an easier way to do it. That doesn't, hopefully doesn't leave the reader any kind of room for quibbling. So hopefully no trash talking from the readers. Let's see here. Epsilon greater than 0. Notice 1 over 16 epsilon is greater than, is less than rather n prime for some natural number n prime by the Archimedean property. So let big N be the maximum of 20 and n prime, right? Then that means that n is greater than or equal to 20 and n is greater than or equal to n prime, right? And it's greater than 1 over 16 epsilon, right? So in particular, we have that 1 over 16 big N is less than epsilon. And we also get to assume that, little n is larger than 20. Right, because if notice that n is greater than or equal to n, which is greater than or equal to 20. So by transitive property, little n is greater than or equal to 20, which is why I get to drop the absolute value like I do over here in that way, right? So algebra, common denominator, cancel stuff, use the condition n larger than 20 to identify that the top is negative, which means I need to factor out a minus and kill it with the absolute value. There it is. And then we're good to go. See, because I can drop the 20, make it larger, cancel the ends, drop the 4 to make the fraction larger, less than or equal to 1 over 16 big N, which is less than epsilon by our construction. Hence, a sub n goes to 1/4 as n goes to infinity. And again, this is a proof directly from the definition. Okay, so I thought it would be healthy, it would be good for me to, work through those examples in the book on my own and show you a little bit about how I think about them. Because the book doesn't tell you too much about, it's not bad, it's pretty complete, so I won't say more. Here's a lemma. And so what we're going to do for the remainder of this lecture is prove some fundamental theorems about limits, in particular that, they're unique if they exist. There's a comparison theorem, a squeeze theorem, and then finally we'll end with the theorem about subsequential limits, which is one of the principal tools to disprove a limit existing, actually, more than proving it does exist. But anyway, let L be non-negative. If L is less than epsilon for all positive epsilon, then L is equal to 0. So here's my proof. Suppose L is greater than or equal to 0, and L is less than all positive numbers. Well, if L is greater than 0, then epsilon equal to L over 2 is less than 0. Hence, L is less than L over 2, which is just nuts. Therefore, L is equal to 0. Because remember, it's either equal to 0 or it's greater than 0. If it's not greater than 0, it must be equal to 0 by, them's the cases. Next up, and so we're going to use that lemma 2.1.2, to prove the next theorem. A convergent sequence has at most one limit, or in other words, the limit of a sequence is unique if it exists. So suppose a sub n and b sub n both converge to a and b respectively. Suppose a sub n converges to a and a sub n converges to b. We'd like to show a equals b, right? So let epsilon be positive, then epsilon over 2 is positive. So there exists an n sub a and an n sub b, such that whenever n is bigger than n sub a, we're within epsilon over 2 distance from a to a sub n. And likewise, whenever n is larger than n sub b, we're within epsilon over 2 distance from a sub n and b, like that. And so if we let n be the maximum of n sub a and n sub b, then we get both of these conditions. And so a minus b is, you can add and subtract a sub n. So I did it in kind of a weird way. I don't know what's wrong with me, but anyway, it is true that that's equal. And so that's a sub n minus b plus, this is triangle inequality, less than or equal to the absolute value of minus a sub n minus a, but you can absorb the minus and just get a minus a sub n, or rather a sub n minus a, like that, which of course is less than epsilon over 2 plus epsilon over 2, which is epsilon. And so we've just showed that a sub n minus b is less than epsilon for all epsilon greater than 0, right? And therefore, we find that actually, there's a little bit of a problem. Oh, never mind. It's the absolute value, right? So that shows you, I was worried about thinking about this being L. Well, notice that 0 is less than or equal to an absolute value, right? So I do have my quote-unquote L is non-negative here. So we find that the absolute value of a plus a minus b is equal to 0, thus a equals to b. We're good. Next up, the close cousin to lemma 2.12, which is sort of an epsilonic version of how to, basically how to get less than or equals to in terms of epsilon, I suppose. I don't know what you want to call this thing, but it's pretty slick. A less than or equal to b if and only if a is less than b plus epsilon for all epsilon greater than 0. So the forward direction of this proof is stupidly easy. A less than or equal to b, then a minus b is less than or equal to 0, which is less than epsilon, and that's true for all epsilon greater than 0. So game over, end of forward proof. Now the converse direction of this biconditional, a little bit trickier, but not too bad. Suppose a is less than b plus epsilon for all epsilon greater than 0. I'm assuming that, right? Then certainly a minus b is less than epsilon for all epsilon greater than 0. I just subtracted b to the other side. Great. Now there's two different cases to think about. If a minus b is less than 0, right, then a is less than b, thus a less than or equal to b is true. However, if a minus b is greater than or equal to 0, I mean either a minus b is less than 0 or a minus b is greater than or equal to 0, right? This covers all possible cases. So if a minus b is greater than or equal to 0, then what do we have? Then by lemma 2.1.2, we can identify that L is equal to a minus b, which is greater than or equal to 0, and it's less than epsilon for all epsilon greater than 0. Therefore, L is equal to 0, which says that a is equal to b. Thus, a less than or equal to b is true. So in all possible cases, we find a less than or equal to b is the implication there. So, I think my proof there is a little bit better than the book, but whatever. Maybe not. I don't know. So theorem 2.1.5, here we have two sequences. They converge to a and b respectively, and term by term, a sub n is less than or equal to b sub n, all right? Then the claim is that the limiting values a and b have to be likewise arranged a less than or equal to b. So here's the proof. Suppose a sub n goes to a, b sub n goes to b. Let epsilon be positive, then epsilon over 2 is positive, and so you can get item 1 and item 2, right? You can make the distance between a sub n and a be less than epsilon over 2, and likewise for b sub n minus b less than epsilon over 2. So if we pick n to be the maximum of those two, we get both epsilon minus epsilon over 2 above and below, minus epsilon over 2 below, epsilon over 2 above, a sub n minus a, and likewise for b sub n minus b. This is just unwrapping these inequalities. Remember, we can trade a less than inequality with absolute value for a compound inequality like this. And so of course you can solve these, add a to this one, and add b to that one, and you get a minus epsilon over 2 less than a sub n, less than a plus epsilon over 2, and likewise b minus epsilon over 2 less than b sub n less than b plus epsilon over 2. It turns out all we need is what's in red here and what's in green there. So actually the other half of this story I didn't even really matter. But anyway, I just left it there for giggles. And so there you go. A sub n minus epsilon over 2 less than a sub n is less than or equal to b sub n, because that was the assumption at the start. And that's less than b plus epsilon over 2, which if you look at that, what that gives us, if you add epsilon over 2 to both sides, we get a is less than b plus epsilon, but epsilon was arbitrary, so we've just showed that a minus b plus, a is less than b plus epsilon for all epsilon greater than 0. Therefore, a is less than or equal to b by lemma 2.1.4. Hooray! So that's the comparison theorem. The squeeze theorem is up next. This is a big one. And here it is. If we have a sub n less than b sub n less than c sub n, and a sub n goes to a and c sub n goes to c with a equals to c, or you could just write c sub n also goes to a, whatever. Then b sub n goes to a, all right? So what this is really saying, by the way, it's something that's sometimes missed here, is it's saying that the middle sequence is convergent. So this gives you the convergence of the middle sequence on the basis the convergence of the upper and lower sequences here. There's another version of this theorem where if you can assume the existence of all three of these, drop the insistence that the A is equal to C, and you can still get that A is less than B is less than C. But that's essentially just the comparison theorem done twice, so whatever. This one's interesting because it gives you the existence of the B limit, B sub n limit. All right, anyway. Epsilon greater than 0, A sub n goes to A. That means we can find n sub A such that that happens. Likewise, since C sub n goes to A, we can find an n sub C such that that happens whenever, you know, and I'm missing some words here, whenever n is greater than or equal to n sub A, right? And such that this, I should say, n greater than or equal to n sub C implies, sorry, some fine print there, oops. Let n equal the maximum of n sub A and n sub C, then if little n is larger than that n, then we get both the A and the C inequalities. So we get A minus epsilon less than A sub n, which is less than or equal to B sub n by assumption, which is less than or equal to C sub n by assumption, which is less than A plus epsilon by construction of big N, which then says that minus epsilon is less than Bn minus A is less than epsilon, but this compound inequality gives us this absolute value inequality correspondingly. And hence, since we've shown this for arbitrary epsilon, by the definition of the limit, we get that B sub n goes to A as well. And that's the squeeze theorem. All right, so next up we talk about sequences being bounded. So essentially, you could talk about the range of a sequence. The range of a sequence is just the list of its values. And so basically the range of a sequence is a subset of real numbers. And if that subset of real numbers is bounded above, the sequence is bounded above. If the range is bounded below, the sequence is bounded below. And if the range is bounded, then the sequence is bounded, meaning that it's bounded above and below. So nothing especially exciting there. So in other words, we can all fall back on our, kind of nice double-sided characterization of boundedness. In other words, a sequence is bounded if and only if there exists a positive constant m such that the absolute value of A sub n is less than m for all n. So we can capture boundedness like that. And here's a big theorem. A convergent sequence is bounded. And so I added a picture. Basically, you could think about the black dots as being the, so maybe this would be, I don't know if I've even, whatever scale I'm using here, I don't know what scale I'm using. Maybe that's A1 right there. I'm not very good at my scale is not very linear, but anyway, A sub 1 is there. This would be like 2, 3, 4, I guess that's A sub 5. Alright, so forth and so on. Anyway, the idea here is if the limit of the sequence exists, then that means it's getting very close to A as you go on out, further and further in n, right? I mean, n goes to infinity as we go this way, right? And so the proof, essentially the idea of the proof is just this. Since the sequence converges, you can pick any epsilon you like and like chop it off there, right? So beyond that point, we control the distance from A to A plus or minus that epsilon, so we're probably going to be able to get that to get some kind of bound. And then like below that epsilon, rather below that choice of big N, you can just take a list of those things and just, well, anyway, let me show you the proof here. So here it is. I'm going to use that epsilon. Well, what epsilon? Pick 1. I just chose epsilon equal to 1 for the sake of an argument. So if epsilon is equal to 1, well, that's positive. So that means that there exists a big N such that n is larger than big N implies that the absolute value of A sub n minus A is less than 1, which means minus 1 less than A sub n minus A is less than 1, which means that, well, A minus 1 and A plus 1 are above and below A sub n. So surely if we can see that the absolute value of a sub n is less than the maximum of the absolute values of these guys. All right, great. And then I'll just let big M be the maximum of the absolute value of all the values of the sequence up to right before the big N, and then a sub minus 1 and a sub n, a sub minus, absolute value of a minus 1 and absolute value of a plus 1 to take care of everything past n or equal to n. And that's it. I mean, clearly a sub n is less than or equal to m as advertised. Thus a sub n is bounded. Now, if you look at your book, it's got a slightly different argument. You notice they show that, they argue that a sub n minus a is less than 1, and then they're like, well, this absolute value of a sub n minus absolute value of a is less than or equal to that, because any number is less than or equal to its absolute value, right? And then they're like, well, that is less than or equal to that, referring to a property from a previous section. But remember, this is less than 1, right? So add absolute value of a to both sides, we get that the absolute value of a sub n is less than 1 plus the absolute value of a. So you could use that in place of these two if you wanted. I don't know. Whatever you like more. Anyway, the larger point here is if the sequence is convergent, then it is bounded. All right. Is every bounded sequence convergent? Well, let's find out. We'll find out soon. So next up is the idea of a subsequence. A subsequence of a given sequence is given by basically selecting terms in that sequence, and they have to go on, and here's the way we capture that idea. A sequence B sub n is called a subsequence of A sub n if there exists a sequence of increasing positive integers n1 less than n2 less than n3 da 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 da, such that B sub k is equal to A sub nk for each k in n. So the idea is that the subsequence is essentially like, well, if we think about the range of the sequence, the range of the subsequence is a subset of the range of the sequence. And it also can't be, it's not a finite subset. It has to be an infinite subset in the sense that it goes on and on and on. Although I guess technically speaking, when I say that, I'm dealing with multi-sets, not sets, because a constant sequence, in view of regular sets, would just have like one thing in it, whereas I'm thinking of a multi-set where 1, 1, 1, 1, 1, 1, 1 is just that set with 1 as many times as you have it. I probably need to strike that last sentence from the record. La la la. So sorry. I shouldn't have brought up multi-sets. You wouldn't have noticed if I hadn't. Anyway, a sub n equals minus 1 to the n has subsequences. Well, this is usually called the even subsequence or the odd subsequence. The even subsequence is just 1, 1, 1, da 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 da. The odd subsequence is minus 1, minus 1, minus 1, right? So in particular, the n sub k for this one is 2k. The n sub k for that one is 2k plus 1, and here bk is equal to 1 for all k, and bk is equal to minus 1 for all k for that one. So here's a little lemma that we need to prove our theorem on subsequential limits. It's a sort of a silly looking little lemma, but it's actually really important to what follows. So if you have a sequence of positive integers which is strictly increasing, then n sub k is greater than or equal to k for all k in the natural numbers. We're going to prove this by induction on k. First of all, it's true for 1. n1 is greater than or equal to 1, because n1 is an integer, so there you go. Positive integer, rather. Suppose inductively that n sub k is greater than or equal to k for some k in the natural numbers. And then consider n sub k plus 1. Well, that's greater than n sub k, right, by assumption. And notice that n sub k is what? Well, n sub k is greater than or equal to k. Also, that's the induction hypothesis, right? Okay, great. But we also know that n sub k and n sub k plus 1 and n sub k are natural numbers, right? Thus, and this is where the kind of non-trivial step is, n sub k plus 1 minus 1 is greater than or equal to. Notice that I've got greater than here, I've got greater than or equal to here. And the reason that that's okay, there exists the chance that n sub k plus 1 is the successor to n sub k, then it's just plus 1, right? So if I subtract 1 from n sub k plus 1, at worst, it could be equal to n sub k. It could, if it's more than 1 past n sub k plus 1, then it could be like, still have a strict inequality here, but certainly it's greater than or equal to n sub k plus 1 minus 1. But that's greater than or equal to k, and so adding 1, we get n sub k plus 1 greater than or equal to k plus 1. Therefore, we've established the induction step, and the lemma is true by proof of mathematical induction on k. And so that brings us to theorem 2.1.9. Let me pause for a drink here. If a sub n converges to a, then any subsequence a sub n k of a sub n likewise converges to a. So suppose we have a sequence a sub n converging to a, let epsilon be positive, and then we can choose n in the natural numbers such that when little n is larger than big N, we get a sub n minus a is less than epsilon. Great. But for any k larger than or equal to n, we also have that n sub k, and so I think what my proof is missing is, I usually try to write the proofs in being complete. I think I've forgotten to, it's a question of style whether or not you reference the theorem in the proof, or I don't know. My proofs are slightly clumsy usually because I actually include stuff like this. Suppose a sub n converges to a and has subsequence a sub n k. All right, there we go. Period. All right, because I'm referring to that subsequence all of a sudden, And well, really, I'm referring to the index function of the subsequence. N sub k is the index function of the subsequence. So we have that n sub k is greater than or equal to k by the lemma that we just proved. And so likewise, we obtain that a sub nk minus a is less than epsilon, right? Because it meets the condition to be larger than n, right? So therefore, we have shown that an arbitrary term in the subsequence is less than epsilon distance, and this epsilon was arbitrary, so it follows that the limit as k goes to infinity of a sub nk is equal to a. So there you have it. Now, what that is most interesting is if there exists a subsequence of a given sequence which does not converge, then it must be that the sequence does not have a convergent limit, right? Or if we have two subsequences which converge distinctly, like a sub nk goes to a, but a sub mj goes to a prime, and they're not equal, then a sub n diverges. That's sometimes a very useful way to get around dealing with a particularly cranky sequence. And going back to my question, do all bounded sequences converge? Well, here's an example. No. Certainly the absolute value of a sub n is less than or equal to 1 for this one, right? So it's definitely bounded sequence. It's going back and forth between 1 and minus 1. But the even subsequence goes to 1, whereas the odd subsequence goes to minus 1. Therefore, that a sub n is a divergent sequence. It does not converge. So caution, beyond this point, sequences are allowed to start at things other than 1. Just so you know, something like 1 over n minus 1 times 1 over n minus 1 times n minus 2 would have a domain of like 3, 4, 5, so forth by convention, and we'd write something like 1 over n minus 1 times n minus 2 from 3 to infinity, if we wanted to be specific about that. Alright, so there you go. That's the start of Chapter 2, and next time we'll move on to what are sometimes called limit laws, or limit theorems. Thanks, guys.